Before I forget, wouldn't that be bad if I didn't record? Oof, limits. We don't want to deal with limits quite yet. Not until we're in calculus. Okay. Math 120. Okay. So, last day we started talking about the domain of a function, right? And so let me just get back there. So just as a little bit of review, right? We started 1.4 specifically talking about the domain of a function. Specifically talking about the domain of a function. Oh, I'll clean that up. Okay. We said, okay, well, the domain is all the possible values of x that we can have, right? And so the domain is all possible values of x. Right, all the possible inputs that we can have. And so we said, well, there's a couple of things that we need to keep in mind, right? That we can't divide by 0. That's a big one, right? So any x that makes us divide by 0 is not in the domain, right? And so first one to keep in mind is that we can't divide by 0. Right? Which means any x that makes you divide by 0 is not in the domain. So any x that makes you divide by 0 is not in the domain. The second rule that we have to look at and remember is that we can't take the square root of a negative number. We can take the square root of 0, right? But anything less than 0, we can't take the square root of, right? And so we can't take the square root of a negative number. Right? So what that means is that any x less than 0, right, is not in the domain. Is not in the domain. Right? If we're talking about the square root of x, right? And so if f of x is the square root of x, right? But in general, right, anything under the square root that is less than 0 is out of the domain. Any x that makes the value under the square root less than 0 is not in the domain. Maybe turn your cell phone down. So those are the two main things that we're gonna keep track of, right? Later on in the course, we're gonna add a third one, right? When we get into logs kind of more deeply. But for now, let's start with just these two main rules. And as long as you remember these and look at these and know that I cannot divide by 0 and I cannot take the square root of a negative number, that's going to go a long ways. So, and then we looked at finding the domain of things, and I'm pretty sure I remember doing kind of a biggie, right? We did kind of a big problem. There was a square root in the numerator, and then in the denominator we had x plus 1. I'm pretty sure I'm looking at it here. Can't do that again. We just did it last day, right? And so maybe go back and have a look at that just to see. But that's about as bad as they'll get, right? You'll have to keep track of the numerator and the denominator and then combine those domains for the domain of the whole thing. Jenna, who's teaching the other section, and I, we got together on Friday, and because there is a final exam that exists for this course, and so we decided, let's save some time and some energy, and if it's not on the final, how about we don't really waste our time on it, unless it's building towards the final, okay? So what we decided to do was something like 1.7, if you've had a look at it. It doesn't really introduce anything new, it's just a bunch of word problems. And I think you'll be happy to know that there is not a single word problem on the final exam. Nice. It's just going to be do this math, do this math, do this math, do this math, which, I mean, word problems are fun if you have time and you can look it up and you can kind of think about it. Word problems are not that fun in a test situation. So, so I was pretty excited by that because I can't teach you how to solve word problems. I can teach you how to look out for things. But word problems are kind of tricky that way. And so, so section 1.7, we're not going to spend time going through. What we'll do is we'll just kind of change gears and just focus on what we need. And of course, only the things that we've talked about in class will be tested on the tests and the final, right? And so that way we can kind of drill it down because there are a lot of extra concepts and kind of fun ideas. So what you'll see when I made the notes for section 1.8, for example, is at the end there's optional material. That's something that we're not going to go through in class, but if you want to have a look at it, sure, you've got the resources, but you don't have to, right? And so if it's labeled optional, that's exactly what it is, right? So it's not something that I'm going to throw on a test or anything. No, I'm not going to do that. Only things that we've talked about in class are going to be tested. Okay? Those WebAssign assignments, right? They might push you a little bit, right? Those little quizzes that you have to do. But that's because you've got time. You can talk to your friends. You can look things up, right? You can look through our notes. You can talk to me, right? And so you've got time and just kind of the freedom to look it up. So those I don't feel bad about, trying to push you a little bit, right? But yeah, anyways, so changing gears a little bit, because chapter 1, there's a lot of stuff in there. It's basically all of math, all the rules of math that we're going through, which is really good. Also a little bit tricky. Okay? So I was looking at the next few little bits in 1.4, and you know what I decided? Because they haven't introduced the quadratic equation yet, so the quadratic formula is introduced in 1.5, but it's going to make everything so much easier that what I want to do is I just want to introduce the quadratic equation, especially because we've got the notes, right? So we can just flip around a little bit, okay? But if we skip to section 1.5, so skip to your notes on 1.5, specifically on the second page and the quadratic formula, the rest of the questions in section 1.4 will be a lot easier to solve. The rest of the questions in section 1.4 will be easier to solve. Yeah.
Will we be reviewing completing the
completing the square?
Yeah.
No, I'll leave it until we need it.
Okay.
Yeah. So when we need it again, then I'll bring it up and review it. But yeah, so okay. So then if you skip to your 1.5 notes and we talk about, well, what is a quadratic equation, right? First, if I'm telling you that this thing is going to make our life easier, we should probably know what it looks like, right? And so if we see something like, so a quadratic equation, and this is from your notes, so you don't really have to write it like this, looks like, I'll scoot this down here. Guess I could have stolen it. I'm on a roll. Looks like ax squared plus bx plus c equals 0. Okay. This is a quadratic equation. So if you see something like this, or specifically something like ax squared plus bx plus c, right, then we're able to use the quadratic equation, the quadratic formula, to solve for the roots. Okay. Solving for the roots is solving when this function is equal to 0, right? And so what we can do is we can use the quadratic formula to solve for the values of x that make ax squared plus bx plus c equal to 0. So we can use the quadratic formula to solve for the values of x that make ax squared plus bx plus c equal to 0. If we're thinking about it graphically, this would be saying, well, I'm going to solve for the values of x that make this function 0. So essentially where it's going to cross the x-axis, right? So this is going to be all the points where ax squared plus bx plus c cross the x-axis. And we can use this for any ax squared plus bx plus c, right? So a can be anything, b can be anything, c can be anything, right? As long as it's a real number, we can handle it, right? And so the formula says that, okay, well, the values of x here, if you think about x squared, right? X squared is this parabola, right? And so at most, if we shift this parabola down beyond the x-axis, right, this function is going to cross the x-axis at 2 points, right? And so what we're going to get is potentially we're going to have two roots, right? So two functions or two values of x where it crosses the x-axis at most. Okay? And so what we get is we get x is equal to negative b. So you pull that b from the equation, right? Plus minus, meaning so for one portion you're going to use the plus, and then for the other value you're going to use the minus, right? And so that's what gives us these 2 points, plus minus, and then the square root of b squared minus 4 times a times c, all divided by 2 times a. So if we pull from one of the quadratic equation problems, right? If we steal, I don't know, should we do the last one? 80. Doesn't matter. Although something tells me there's going to be no solutions. But anyways, doesn't matter. Let's try it. Because what's it going to look like? Right? Even if you've got something like this, right? X squared, it's been bumped down, right? Here's probably, there's the negative portion and there's a positive portion, right? So here we have two solutions for x. There are instances, right, where you have something like this, well, that never crosses the x-axis, right? And so we have no solutions for x. And something tells me that that last one is going to be no solution. So then we'll go down, we'll hunt one down that has solutions so that we can try both. But let's have a look at 80. Find all real solutions of the quadratic equation. So we've got 25x squared plus 70x plus 49 equals 0. Okay. Rewriting this as a times x squared plus b times x times plus c, I get this is my a, this is my b, and this is my c. All these are adding, right, or positive, and so I can just use the values as a, b, and c. Which means that I can write, okay, well, x equals, and I'm going to write out my usual equation. Oh, not b squared, not yet. Negative b, sorry. Negative b plus minus the square root of b squared minus 4ac over 2a. Don't worry, you will have it memorized, but also it will be on your formula sheet. So, but you'll use it so much because it does make your life a lot easier that you'll remember it. Yeah.
Isn't there a way you can do like adds to the
Mm-hmm. If you like that way, great. I personally have a hard time with that, being able to figure out. So with easy numbers, yeah, sure. So you have to think of two numbers that multiply to one thing, but also add to another thing. That can get pretty weird, right? And so in this case, sure, right? But at least with the quadratic formula, I'll be able to tackle any value, right? And so so that's why I prefer this way. But definitely, if you're comfortable being able to say, oh, well, I can factor that into this, right? That's fine, right? But if you're like me and you have a hard time seeing those values, right, or arriving at them quickly, this will always work. Right? So from here, I'm going to plug in, so x is going to be negative b, so negative 70 plus minus the square root of 70 squared. Remember, the square of a negative number is just going to be a positive number, even if your calculator tells you otherwise. So if you do negative 2 squared, depending on how clever your calculator is, it might tell you it's negative 4, but that's because it's pretending that the negative is on the outside, right? So you'd have to wrap it up in brackets, or just remember that it is actually a positive value. Right, and so 70 squared is going to be positive anyway, so it doesn't matter. Minus 4 times a, which is 25, times c, which is 49. All over 2 times a, which is 25. So we can simplify this a little bit. I'm going to leave the negative 70 on the outside here, plus minus, and I'm just going to simplify under the square root for now. So 70 squared is 4,900 minus 4 times 25 times 49 is going to be pretty big. Just big enough. Nice. Divided by 50. For being the last problem, come on. I thought I was picking a moneymaker. No. So then we have negative 70 plus minus 0 over 50. Making sure that your square root, right, you can't take the square root of a negative number. If you find yourself having to take the square root of a negative number, you've probably missed a negative somewhere, right? Because that'll never happen. Okay? And so, yeah, so if you find that that's happening, then
Isn't that an imaginary number?
It is an imaginary number, but in this course, we're not getting into those. So for us,
If you've got a negative, you've done something wrong.
yeah, then something happened and we can't do it. So yeah, no, we're not getting into imaginary numbers, only real numbers. So negative 70 plus or minus 50. So 70 divided by 50, x is, and I'm going to do a squiggly equals because it's a decimal approximation. It's still exact, but whenever I'm converting a fraction into a decimal, right, I just want to remind myself that hey, this is an approximation, right? Yeah.
Would you not still get two values of x equals to negative 1.4 because you have to do one where you plus the 0 and one where you subtract the 0?
But they're both.
Yeah, because
Equal, but I'm wondering if you have to write down 2 for the answer or just write one.
no, just one. Because negative 70 plus 0 is the same as negative 70 minus 0. Yeah. What that would look like.
Yeah, that's fine.
Something like this. Or what if it just starts at negative 1.4? Right? So another option might be, what if it looks like here you're at negative 1.4 and it just, that's where it started maybe. That's the only thing I can think of. Otherwise, if you scoot it down a little bit, you're going to have 2 points on there. So, nice. I wanted to do another one that would work out. How about, let's do 66 because, well, it's among the beginning ones, and so it should just give us two numbers. So let's give it a go here. We've got x squared plus 5x minus 6 equals 0. So now a is equal to 1, b is equal to 5, and c is equal to negative 6. Right, so don't forget that negative. Then we can solve x is equal to negative b plus minus the square root of b squared minus 4ac all over 2a. Let's give that a go. Negative 5 plus minus the square root of 5 squared minus 4 times 1 times negative 6 over 2 times 1. I get negative 5. 5 squared is 25, so plus minus the square root of 25 minus, but then 4 times 1 times negative 6 is also going to be negative, right? So if we do plus, right, then we can just do 4 times 1 times 6, making sure you keep track of your negatives, right? So 4 times 1 times 6 is 24. Right? All over 2 times 1, which is 2. So 25 plus 24, negative 5 plus or minus 49, divided by 2. Okay. Puts us at negative 5 plus minus 7 divided by 2. Right? If we're lucky, then that square root goes away. We don't have to deal with it anymore. So now, all along here, x equals, x equals, x equals. As a rule, you don't have to write it out, right? As long as you've got the x equals on the left-hand side at the beginning, then as long as nothing's changing, you don't actually have to fill in the left-hand side. You can just have equals, equals, equals. And then it's assumed that nothing's changing on that side. So now, if we boil this down, so then x equals negative 5 plus 7 over 2 and negative 5 minus 7 over 2. So x is negative 5 plus 7, which is 2 over 2, which I'm just going to write as 1. And negative 5 minus 7 divided by 2 is negative 6. Just using your calculator or using your head, doesn't matter. So now, x equals 1 and x equals negative 6 would give us the whole thing equals 0. Right? So those are the values that yield 0. And so what we can do, therefore, x equals 1 and x equals negative 6 make the original equation x squared plus 5x minus 6. I'll scoot this down to a new page. Make x squared, is it plus 5x? Yeah, plus 5x minus 6 equal to 0. Which means, and this is the key, and this is why it makes our life so much easier if we just know how to use it, which means that we can rewrite x squared plus 5x minus 6 as something else. Which means we can rewrite and say that x squared plus 5x minus 6 is the same as x minus 1 times x plus 1, or plus 6, sorry. Okay. Because regardless of which one we use, right, x equal to 1 plugged into here apparently yields 0. X equals to -6 plugged into here also yields 0. That's what we decided. That's what the quadratic formula told us. But that means that if you can't see how to factor this, right, then knowing where x or what x's make this 0, well, I can just take x minus 1, right? So usually you just take the opposite of x equal to 1. Well, then if x is 1 minus 1, this whole thing would go to 0, right? -6, same deal. -6 plus 6, 0. 0 times whatever is 0. Right? And so I use the quadratic formula a lot to try to factor things out, right? Remembering that if I can rewrite, and I just kind of think of it as the opposite, right? X equals +1, then I need x minus 1, right? X equals -6, then I need x plus 6 here to make 0. So I'll do a little. I'm gonna draw my arrows here. Whee! Yeah. Even if later when we get kind of fractional roots, so just as a note, the solutions to ax squared plus bx plus c equals 0 are called roots. Or zeros. Because I realized I've been saying roots without really defining it. And so, so that's where they are. Okay. Especially if you're looking at something like ax squared plus bx plus c, and you have to solve for x, at least we have the quadratic formula, so we can just skip that step. Right? And you can do it. In fact, the notes go through and show you how to do it. You do have to complete the square, but like I said, we're not actually gonna, they do it in the background. We've got the formula, we can just use the formula right away. Right. Any questions? No? Okay. So, in your notes, right, the end of 1.5 talks about the discriminant. The discriminant I would label as optional. It's not going to come up on the final. It's just a way of figuring out how many solutions you have, right? We talked about, okay, well, we saw a situation where we have one solution, we could have two solutions, or we could have no solutions, right? And so it's just a way of figuring out how many solutions you have, right, or are expecting to get. And so the discriminant is optional. We will not cover the discriminant because it is not on the final. Right. but it's just a quick way to figure out how many solutions you're expecting to have. Right? It won't tell you what they are, but it will tell you how many to expect. May as well go back to jumping around. I know you've got the notes, so it's not that bad. What if we just kind of take a load off and solve some linear equations for a little bit? We went to quadratic equations because it turns out that we need them in 1.4, at least to make our life easier, right? But let's just finish 1.5 so that we can finish on a high note in here. So a linear equation is just a straight line, right? So remember y equals mx plus b, right? M is the slope, b is the intercept, the y-intercept. So we can solve linear equations just like we solved quadratic equations just now. Right? And so solving linear equations is when you have something like y equals mx plus b. This is a linear equation. Linear equation. And remember that whatever is attached to the x is the slope. And whatever's on its own is the y-intercept. Yeah. Solving the linear equation means finding the x where it crosses the x-axis, right? So it means finding the x-intercept. So solving a linear equation means finding the x-intercept, right? And the x-intercept is where the line crosses the x-axis. The x-intercept is where the line crosses the x-axis. Just like we did for quadratics, but now we're kind of going backwards and talking about an easier thing, but that's okay. All right, so same idea, it's where it crosses the x-axis. And so solving a linear equation just means where is it going to cross the x-axis, right? We can find things just from the equation, we can find the slope and we can find the y-intercept, but if we solve it, we're able to find the x-intercept. And so if we have something like ax plus b equals 0, we need to be a little bit flexible, right? And notice that whatever is attached to the x is your slope, and whatever is on its own is the y-intercept, right? Because that's the equation that you have for the linear equation when we're trying to solve it. So it doesn't matter if you use mx plus b or ax plus b, or if you go into statistics, you'll use probably b1x plus b0, something like that, right? It doesn't matter, as long as you kind of keep in your mind that whatever is attached to the x, that's the slope. Whatever is on its own, that's the y-intercept. All right. Or even if you're heading into, if you're in business, right, you've got those supply and demand curves, right? Those would be straight lines typically, right? And so anytime you've got a straight line graph, you've got a linear equation. All right, so what if we have to solve some of these? Let's see here. I know you guys want the last one, so let's just do it. 30 is the root of 3 times x. Notice that x is not under the square root. All right. And just to emphasize that, I put a little tick down to kind of close off the 3. And that's more a reminder to myself so I don't get carried away and do the square root of 3 times x, because that's not what I want. I want the square root of 3 times x. I know it sounds the same, but it's different. So the square root of 3 times x plus the square root of 12 is x plus 5 over the square root of 3. I want to solve for, well, what values of x is going to make this 0, right? All of this 0, which means that, okay, well, if I want to get it into some sort of form, right, I need to get 0 on the one side, right? I have to have 0 on one side, move everything else to the other side, and then I can try to figure out what x has to be. Okay. And so what we get, right, if we start moving things over to the left-hand side, for example, right, mostly because I want to get rid of that square root, the square root of 3 in the denominator. So the kind of next step would be to multiply both sides by the square root of 3. So what that's going to look like is we've got the square root of 3 times the square root of 3x plus the square root of 12, right? Because this guy got multiplied to there, right? Makes sense to me to draw the arrow that way, but kind of, I guess technically it got multiplied over to here. For multiplying both sides by the square root of 3, right, just to show what we're doing here until we get a handle on it, x plus 5 over the root of 3 times the root of 3. You know what? I'm going to do this root of 3 in a different color just to emphasize, and then we don't need this confusing arrow. Sure, let's use pink. All right. If I have a true statement, 1 equals 1, I multiply both sides by the square root of 3. 1 times the square root of 3 is still equal to 1 times the square root of 3. Whatever I do to one side, I have to do to the other side, right? And so that's one of the major things that I see later on that goes wrong, right? You forget to do to one side what you did to the other side. Okay? So here, the whole goal of multiplying both sides by root 3 is because now that I'm multiplying, right, I've got this times this, then I can cancel this root 3, and so now it's gone away. And so how I imagine it is it just traveled over here, right? For future work, we're not going to show this portion, right? I'm just showing you where it came from because it's been a while. So this cancels with this. So now we can rewrite this as the square root of 3 times the root of 3 times x plus the root of 12 is x plus 5. We've got a couple of things that we could do, right? We could ignore the root 3 times root 3x plus root 12 and just start moving the x plus 5 over, right? We have to do them individually. So to move the plus 5, I have to subtract 5 from both sides, right? So I'm gonna, let's do that, kind of chip them off. And so we get root 3 times root 3x plus root 12, and then minus 5 equals x plus 5 minus 5. Making sure you do to both sides what you did to one. So that's how you're going to move that minus 5 over. Okay. Same thing with the x. We can move the x over, but x minus x, remember, it gives you 0 on that side, right? And so here we've got root 3 times root 3x plus root 12 minus 5 minus x is x, oops, minus x, which is going to go away. Oh, this is supposed to be pink here. So now I can rewrite this as the root of 3 times the root of 3x plus the root of 12, then minus 5 minus x is equal to 0. Right? All right. So now, we can do it. I'm going to start by multiplying the root 3 inside, right? See what happens. And so we established that root 3 times root 3 would just be 3, right? So if you take the root times a root of the same thing, we just get that thing out. And you can go back to your power laws, but just take my word for it. So root 3 times root 3x plus root 3 times root 12. Now that I've brought that root 3 inside, I don't need the brackets anymore, right? And so now I've got that minus 5 minus x, letting it be 0. So now I can start simplifying and I can say, well, that's the same as 3 times x plus root a times root b. We can rewrite, right, as root a b. Right? That's a rule. Right? Because we're multiplying and dividing only, right, where we can kind of squish together or separate the square root. And so this is going to be the same as 3 times 12 square rooted. And then minus 5 minus x equals 0. Let's deal with 3 times 12 first. 3 times 12 is 36. And so we get 3x plus the square root of 36 minus 5 minus x equals 0. If you wanted to collect like terms with your x's, that's fine by me. I'll leave it till the end. Luckily for us, the square root of 36 is just 6. So we get 3x plus 6 minus 5 minus x equals 0. So now we can collect like terms and we can say, well, 36 minus, 3x minus x is 2x. And so I've got 2x and then plus 6 minus 5 plus 1 is 0. I broke my own rule. If we're solving for x, right? So now we want to know what x makes this true. We're so close, right? Now I can say, okay, well, I'm going to isolate x, right? So now I'm going to move everything to the other side and try to figure out what value of x makes this true. And so now I've got 2x is -1, right? Subtracting 1, but not really showing it anymore from both sides. And so x is going to be -1 divided by 2. And that's our answer.
This is a little different. I took the root 12 and compared that to root 3 times root 4. And then when I multiplied
Great.
3 into it, just cancel out the root 3. I still have the same number. Will that work on all
Totally.
applications?
Yeah, as long as, so here, all right, we could have rewritten root 12 as the root of 4 times 3, right? And then we could have split that root. The square root of 4 we know is 2. Square root of 3 we don't know, but we just leave it as root 3. But then when we bring in this root 3, right, then we've got root 3 times root 3 times 2. But that root 3 times root 3 is going to disappear, and you end up at the same. Right? So then you have 2 times 3, which is 6. Right? So lots of different ways that we could go about doing it. Great. Cool. All right. Any other questions? No? Okay. Then let's kind of backtrack a little bit to 1.4. Now, a lot of these rules aren't that, they're not that bad, right? And we've actually already talked about rational expressions, right? And so if we're multiplying or dividing fractions, we just talked about briefly how they behave. And so we'll do a couple of examples, but not too many, because this is the type of thing that we'll need throughout the course. And so we'll see it, right? And we'll practice it as we go. But for the first one, where it says simplifying rational expressions, I want you to cross out 24. Problem 24 is, it's not too hard, it's just that it's we're going to max out at powers of 2. Let's see here. Where is it? There. Wait. See how there's that x to the power of 3 in the denominator, right? The highest power that I want you to be able to handle is x to the power of 2. Right? And so only dealing with powers up to 2. Okay. Tell me why I'm not concerned about 23 then. Because I can pull out that common x, and then I'm down to a power of 2, and so it's fine. Right? And so don't worry about 24, but let's use 23, and you'll see that it's a lot easier using the quadratic formula, even though it hasn't been introduced yet. But from now on, we'll have it, right? So we may as well use it. Because what you'll see here, right, after we pull out a common x here, we'll have 2x squared minus x minus 6, right, which is in the form of ax squared plus bx plus c, right? Same thing down here, ax squared plus bx plus c. We know how to find the roots of those things, which means we know how to factor those. So let's instead do 23. And it is a bit of a mumbo jumbo, so buckle up. Here we go. We're just trying to simplify this rational expression. So if we've got 2x to the power of 3 minus x squared minus 6x over 2x squared minus 7x plus 6, first thing I'm going to do so I'm able to deal with this thing is I'm going to pull out that common x. There's no other common factors, and so, but I will pull out an x. And if you wanted to pull out a negative, that's fine. It's not actually going to change anything, so I'm going to leave it in. So then I get x times 2x squared minus x minus 6. Leaving the denominator as it is, 2x squared minus 7x plus 6. So then, all right, now I'm dealing with quadratic and a quadratic, right, which means that I can factor these if I just use the quadratic formula, right? And so any expression of the form ax squared plus bx plus c can be factored with the help of the quadratic formula. With the help of the quadratic formula. So what I'm going to do is I'm going to look at each of these quadratics individually and try to figure out what I could factor them into. Hopefully something's going to cancel in there because I do want to simplify this thing, right? And so if I do something like call this A and this B, right, or something like that, then I'll use the color coding, so factoring A, just to indicate that I'm actually going to work with these separately, and then I'm going to put them back in. So A is 2x squared minus x minus 6. If I have the quadratic equation, I've got x is going to be negative b plus minus the square root of b squared minus 4ac over 2a. So x is going to be negative 1, right? And definitely figure out what your a's and b's and c's are, right? Plus minus the square root of negative 1 squared minus 4 times 2 times c, which is negative 6, over 2 times 2. So now I can simplify this a little bit and I can get x is 1 plus minus, and then the square root of 1, and then 4 times 2 times 6, keeping track of my negatives. Right, I've got minus, and then a negative number means plus 48 divided by 4. 1 plus 48 is 49. And so I get 1 plus or minus the square root of 49 over 4, which is a nice number, 7. So 1 plus minus 7 divided by 4, which means that x is equal to 1 plus 7 divided by 4 and 1 minus 7 divided by 4. Which we can calculate and say, well, 1 plus 7 is 8 divided by 4, putting me at 2. 1 minus 7 is negative 6 divided by 4. I can simplify it a little bit. Negative 6 divided by 4, or you don't even have to if you don't want to. And negative 6 divided by 4. Doesn't really change much if I simplify it, so just gonna leave it. All right, so what does that mean? This says that, well, my original equation was 2x squared minus x minus 6. 2x squared minus x minus 6, using that same method that we had before, we can rewrite as x minus 2 times x plus 6 over 4. They're all going to be 0 at the same time. Okay. So up here, right, I'm going to use the x minus 2 times x plus 6 over 4. I'm going to use that in place of a up top here, right? So now I'm going to focus on b, which is 2x squared minus 7x plus 6. 2x squared minus 7x plus 6. Is that what it was? Yeah. Don't want to do all that work for the wrong equation. But now we just do the same thing over again. Right? And so if we're factoring this thing, then I've got x is negative b plus minus the square root of b squared minus 4ac over 2a. Negative 7 plus minus the square root of negative 7 squared minus 4 times 2 times 6. 4 times 2 times 6 is 48. I guess over 2a, which is 2 times 2. So I get 7 plus minus the square root of 49 minus 48, phew, not taking the square root of a negative, over 4. So I get 7 plus minus the square root of 1 over 4. Square root of 1 is just 1. So I have 7 plus 1 over 4 and 7 minus 1 over 4, which means I've got 8 over 4, which is 2 again, and 7 minus 1 is 6 over 4. All right, which means that we can rewrite 2x squared minus 7x plus 6. So 2x squared minus 7x plus 6 is the same as x minus 2 times x minus 6 over 4. And they're all going to be equal to 0 at the same time. All right. Now that we've factored, we can plug them all back in and see where we're at. So let me just steal this that we had from before. Copy. Paste. So this is what we had before. We did some work on the side. Oops, start with blue. And we said, well, we have x, right? Because we almost forgot about that little x that we pulled outside, right? But it's still there. And then times a, which is the pink stuff. So x minus 2 times x plus 6 over 4. So x minus 2 times x plus 6 over 4. B, oh, and then that's over b, which we just decided we can write as x minus 2 times x minus 6 over 4. It's not a lot better, but it's a little bit better, right? Because now, because we're multiplying all the way across here, right? We're multiplying, 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 multiplying. And so this x minus 2 can cancel with this x minus 2. So at least those are out of there. There's no x that I can cancel with. And x plus 6 over 4 is not the same as x minus 6 over 4, right? So we still have to keep that in there, but we can handle that, right? As long as this, oops, x minus 2 is gone, that's nice. All right, we can keep going. Ugh. We can say, okay, well, that's the same as x times x plus 6 over 4 divided by x minus 6 over 4. This type of problem is long, right? But it does test a lot of things, right? Can you use the quadratic formula? Can you figure out what the factors are? And then now we're looking at adding rational expressions, right? So adding fractions, which means we have to have the common denominator. My trick, right, or my preferred trick, if I need a 4 in the bottom here, right, for this x, I need to rewrite x as something over 4. Well, what if I just rewrote it as 4x over 4, multiplying by 1, right? That's allowed. So inside the brackets, I'm looking at x times 4 over 4 plus 6 over 4. And then I'm going to do the same thing in the denominator. Inside the brackets, although they're not really needed here, but it's okay. I've got x times 4 over 4 again, because I need this also to be over 4, plus 6 over 4. I'll make a note here that I'm multiplying by 1. Right, 4 over 4 is 1, so I'm allowed to do that because it's not going to change the value. Because multiplying fractions, then we can just smush them together, right? It's when we're adding and subtracting that we're not allowed to just smush them together willy-nilly. So if we just keep the x on the outside, then we have 4x over 4 plus 6 over 4 all over 4x over 4. Hey, one of these is minus. That's important. Minus 6 over 4. I forgot I had this as a plus, but it's actually minus. Now that I've got that common denominator, now I'm allowed to go ahead and combine these terms. And so I've got is x times 4x plus 6 all over 4 divided by 4x minus 6 all over 4. All right. I can rewrite this, right? Because I've got a fraction divided by a fraction. So now I'm going to flip and multiply, right? Because that's how we said we have to deal with a fraction over a fraction. And it's even in the following notes, right? On the next page, you've got a over b divided by c over d is the same as a over b times d over c. So you flip and multiply. So times 4x plus 6 all over 4 times, and then flip that bottom. So now the 4 is on top, divided by 4x minus 6. Phew. Because I'm multiplying all the way across here, right, I'm allowed to cancel this 4 and this 4. So now I can rewrite this as x times 4x plus 6 divided by 4x minus 6. There's still a little bit more that we can do to simplify this. Remember, simplifying was the name of the game. 4 and 6 have a common multiple of 2, right? So we can pull out that common multiple of 2, and we can rewrite this as, okay, well, that's x times 2 times 2x plus 3 divided by 2 times 2x minus 3. Again, because I'm multiplying across, I'm allowed to cancel that 2 out from both the numerator and the denominator. So now x times 2x plus 3 divided by 2x minus 3. There's nowhere else to go. Whoa. Okay. So yeah.
Would you just leave it like that, or would you multiply by x?
I'd probably just leave it like that. It's okay. If you brought it in, that's fine too, but it actually doesn't change them. Like, it doesn't change it that much. So I would know what you did if you did. So there's no wrong way from here, right? If you wanted to bring that x inside, it's fine. But I'm just lazy, so I'm calling it quits. All right. Any other questions about that one? It's a big problem, right? But it is a lot easier, and I mean a lot easier, if you've got that quadratic formula, because that's how we were able to factor it. And because to me, being able to factor into something like x minus 2 times x plus 6 over 4 is not obvious, right? But at least if we've got the quadratic formula, then we can just go through and do it, churn it out. Okay, so looking through the notes for the rest of 1.4, the one we just did is a lot harder than 38 for the next section, for example. But we could do it. If we did 38 we have x over y over z, we have to rewrite this, right? And do the division. Well, that's the same as saying, well, that's the same as x over 1 divided by y divided by z, right? So we've got a fraction over a fraction. To simplify those, we have to flip and multiply. So we've got x over 1, right? And that over 1 is, let's call it silent, right? I put it in there just to emphasize that just x, we could rewrite that as x divided by 1, and nothing's really changed. And so x over 1 times, and then the y over z is going to flip to be z over y. And now we're multiplying two fractions, which means we can just smush them together. And so we've got x times z over 1 times y, which I'll just write y. And that's it. And there's no numbers to deal with, and so there's nowhere else for us to go. If we wanted to write them all in the numerator, right, we could rewrite it as x times z times y to the negative 1, but it doesn't really change anything. So if we're adding or subtracting fractions, we just did a big one of those, right? And so that's when you need to get that common denominator, and then you're able to work through it. Let's go into compound fractions, because it's also adding and subtracting fractions, and so it kind of combines all of it. So in compound fractions, let's do number 72. Because it's a little bit nasty. So we're supposed to simplify 1 plus 1 divided by 1 plus 1 divided by 1 plus x. Oof. We have to be careful at every step here. What did I get myself into here? No, it's gonna be okay. Okay. We'll start at the very bottom, right? And try to kind of work our way up and kind of, I always imagine just kind of rolling it up until it's simplified, right? So it's not fractions over fractions over fractions over fractions, right? We can simplify them and just kind of work our way up the ladder. And so what we have is we have 1 plus, but at every step we have to write out all the other terms, right? And so even though it's tedious, 1 plus 1 divided by 1 plus 1 over 1 plus x. I didn't change anything here. What I'm going to do is I'm going to put these guys over the common denominator of 1 plus x. And to do that, I'm going to multiply this 1 by 1 plus x over 1 plus x, right? Multiply by 1. So I'm going to scoot this over here and then say 1 times 1 plus x over 1 plus x. So again, I'm just multiplying that 1 by 1, which doesn't change, right? I'm just able to now eventually combine these into a fraction. So I have 1 plus 1 divided by 1 times 1x is, or 1 plus x is 1 plus x over 1 plus x plus 1 over 1 plus x. I've got that common denominator, and so I'm able to add or subtract the tops, right, the numerators. And so I've got 1 plus 1 divided by 1 plus x plus 1 over 1 plus x. All right. I'm going to simplify this and say, well, that's 1 plus 1 divided by 2 plus x plus 2. Doesn't matter. Let's leave it as 2 plus x all over 1 plus x. Okay. Now, 1 over 2 plus x over 1 plus x, I can rewrite 1 as 1 over 1, and then I've got 1 over 1 over 2 plus x over 1 plus x. That's a fraction over a fraction. So now I can flip and multiply. And so what I can do is I can say, well, that's the same as 1 plus, and here's where I'm rewriting 1 over 1 over 2 plus x over 1 plus x. I'm just rewriting this one here as a fraction so that I can visualize a fraction over a fraction. But if you don't need that, that's fine, right? I just like to always have a fraction over a fraction before I multiply them, or flip and multiply. So here we get 1, which is kind of on the outskirts now, but 1 plus, and then we're going to have 1 over 1, and then times, we're going to flip the fraction in the denominator and say times 1 plus x, which is all one thing, over 2 plus x, which is all one thing. Has to be treated as one thing. Oh, now we're multiplying fractions, which we can just multiply across, that's fine. And so what we get here is we get is equal to 1 plus 1 times 1 plus x is 1 plus x over 1 times 2 plus x is 2 plus x. Now, same idea, right? I have to get this over a common denominator. I'm going to do that by changing that initial 1 to 2 plus x over 2 plus x. Technically 1 times 2 plus x over 2 plus x, right? Whichever way you want to look at it. So this is going to be 1 and then times 2 plus x over 2 plus x. Convince yourself that 2 plus x over 2 plus x is just 1. Right? 1 times 1 doesn't change anything. So that's why it's allowed. Plus 1 plus x over 2 plus x. Can simplify that left-hand term to be 2 plus x over 2 plus x. And then plus 1 plus x over 2 plus x. Now I can combine these. We're so close. 2 plus x is our common denominator, right? So now we've got 2 plus x plus 1 plus x all over 2 plus x. Scoot this down here. New page. 2 plus 1. I can do 3 plus, and then x plus x is 2x. And then divided by 2 plus x. We did it. Right. We simplified this thing. I don't see anywhere else that we could go. There's no obvious factoring or anything that we could simplify it even further. This is it. All right. Unless you guys see something. I don't see anything. All right. Cool. I want to do number 73. And we'll do more of these later and just kind of see where they came from. But for now, I just want to look at how would we simplify something like this. And so if we have to simplify 1 over 1 plus x plus h minus 1 over 1 plus x, all divided by h, what would that look like? So I'll give you guys a couple of minutes to try it on your own, because as it says, these are things that will come up in calculus and I mean any higher level math that you do. So good to get a handle on. All right. Let's see where we got to. So 1, if you're still working on it, that's fine, but just get started here by writing out, because I suspect I'm going to need a lot of room on the right-hand side. First thing I'm going to do is I'm going to get a common denominator in the numerator, right? How I'm going to do that, and for me, this is my, again, it's my go-to trick, right? If I need 1 over x and 1 over x plus h, I don't even bother looking at it too much. I just say, well, this term I'm going to multiply by 1 over x over 1 over x. And this term I'm going to multiply by 1 over x plus h over 1 over x plus h. So you can spend time going through it. But for me, I just, okay, I need to have this guy over here and this guy over here is kind of how my mind works, at least. Yeah.
Can you just multiply the right side by h?
Yes. But no, the right-hand side.
Or no, then I would be.
Yeah, because then you're getting h over and it doesn't. So sometimes you can find little things like that, right? But for me, like I said, regardless of what's going on down here, I just blindly just take this, turn it into 1, right? So rewrite it as 1 plus x over 1 plus x, multiply it over here, and take this guy and do the same thing. So it's going to look like this by the time I'm done with it. 1 over 1 plus x plus h. The new thing here is times 1 plus x over 1 plus x. That's still times 1, right? I'm allowed to do that. Minus 1 over 1 plus x times, and the same idea, right? 1 plus x plus h over 1 plus x plus h. As I suspected, ran out of room a little bit there. And then remember that all of this is over h. Now I've got a fraction multiplied by fraction and then subtracting a fraction. But what we'll find is that the denominator of these fractions is going to be the same, right? And so what I'm going to get is I'm going to get 1 plus x over, and then I'm going to rewrite the denominator so it's in the same order so that I can see that they're common. And so I'm going to rewrite this as 1 plus x times 1 plus x plus h minus 1 plus x plus h over 1 plus x times 1 plus x plus h. That's all legal. All over h. Now, doesn't matter how nasty that common denominator is, right? Now I can kind of look at this and say, well, I can combine these things. And so what I'm going to do is I'm going to have 1 plus x, keep those in brackets even though they're not really needed, but I just want to visualize them as one thing, minus 1 plus x plus h, all divided by 1 plus x times 1 plus x plus h, all divided by h. Okay. Here's where things are going to start to get better. Because as a rule, if we have something set up like this, the h is going to cancel, right? So the h is going to go away. All right. So we can simplify the numerator of the numerator, right? And so we can say that, well, if we get rid of the brackets, keeping in mind, though, that it's 1 plus x, that's fine, minus all of that, right? So you have to bring that negative onto each of the terms inside the brackets. So we can rewrite this as 1 plus x minus 1 minus x minus h. No, we can't, because unless you're able to pull out a common 1 plus x from this one, we can't say that 1 plus x cancels here, because in order to cancel it from the bottom, we have to have a 1 plus x over here. Right? And so that's just the rule that says, okay, well, if I'm canceling, I have to be canceling from both of these. Right? Short answer, no. Because 1 plus x is not a multiple in the second part. Right? And the reason, just to write it over here, right, if you talk about it in terms of a plus b over a, you can't cancel out the a's. You could rewrite it, you're allowed to rewrite it as a over a plus b over a, which is 1 plus b over a, but that 1 plus x, which is our a in this case, would still be hanging around. So that's why. Okay. What I'm gonna do is I'm gonna leave the denominator as is, because hopefully we won't have to deal with it too much. And so I'm gonna leave it for now, hoping that things will cancel later. 1 plus x times 1 plus x plus h all over h. Looking at the numerator of the numerator, we've got 1 and then minus 1, so that's going to go to 0. And then we've got x minus x. Now I've got just negative h up top. So I've got negative h over 1 plus x times 1 plus x plus h all over h. Thinking of that all over h as all over h over 1, right now we've got a fraction over a fraction again. And so what that's going to look like is negative h over 1 plus x times 1 plus x plus h times h over 1. Nope. Haha. 1 over h. I guess I should do it in the light blue that I have been using when I change things, because it was h over 1 and then I flipped it and I multiplied it. So times 1 over h. Now, because everything is being multiplied by h in the numerator, or sorry, in the denominator, then I'm allowed to cancel. Okay. And so here, I'm allowed to cancel this guy with this guy. So now I have negative 1 over 1 plus x times 1 plus x plus h. We should probably simplify the 1 plus x times 1 plus x plus h. I'm going to leave it. Be a little lazy. How about that? Any questions about that one? Oh. Not a one. Okay, so just to recap, section 1.7, do on your own, right? Not tested, right? It might be on your assignments, but it's not going to be tested. 1.8, we will do next day. Same with 1.10, we'll do next day. But 1.11, I'm going to do on your own. It's just showing you how to graph stuff. I'll show you how to use Desmos if you haven't used it before. So I will show Desmos, but then do on your own. Which just means it's not going to be tested. Okay? All right. See you guys on Friday.